Dear students, this is the project Knowledge Rise. I am Ostap Zgalat-Lozynskyi, and we continue our lectures in the course Advanced Materials Manufacturing, lections number 2, Critical Challenges in Scaling Advanced Materials. The field of ceramics had advanced significantly from traditional clay-based materials to modern technical ceramics used in aerospace, energy, electronics, and biomedical applications. These advanced ceramics exhibit exceptional properties such as high hardness, corrosion resistance, and thermal stability. However, despite their desirable characteristics, the scale up from laboratory production to industrial manufacturing remains one of the major challenges in the ceramic industry. The transition involves complex interactions between materials, processing conditions, and manufacturing technologies, often leading to bottlenecks that limit production efficiency, yield, and cost effectiveness. All of this described by so-called technology readiness level, so-called TRL. Scaling up ceramic processing is not simply a matter of increasing batch size. It requires maintaining microstructural uniformity and mechanical properties across larger volumes. Key challenges include material uniformity, maintaining consistent particle size distribution, dispersion, and composition during large-scale mixing is critical. Minor inconsistencies can lead to density gradients and defect after sintering. Sintering complexity. The sintering process essential for achieving full density and strength becomes harder to control at scale. Variations in furnace temperature, atmosphere, or heating rate can cause uneven shrinkage or residual stresses. Equipment limitation. Laboratory furnaces and mixers may not directly translate to industrial system, necessitating reoptimization of parameters. Economic constraints. Scaling up on also increases production costs due to high energy consumption, specialized equipment, and strict quality control requirements. Thus, ceramic manufacturing requires careful process adaptation and continuous monitoring to prevent performance loss during scale up. And we discuss it for advanced ceramic. When conventionally it used as powder processing and forming bottlenecks. Powder preparation and shaping are crucial steps that determine the final product's quality. In large-scale manufacturing, these stages face several bottlenecks. Powder agglomeration, the first bottleneck. Inconsistent mixing and deagglomeration lead to inhomogeneous packing density. The next bottleneck is form methods. Traditional pressing and casting techniques are slow, while advanced forming methods like injection molding or additive manufacturing face throughput and cost limitation. It's not so fast too. Binder systems. Scaling binder burnout in large parts can result in cracking or warping if not properly managed. The optimization of powder rheology and compaction behavior is essential to overcome these issues. The next bottleneck is sintering and thermal processing limitation. Sintering is one of the most energy intensive and technically demanding steps in ceramic manufacturing. Common bottlenecks here include temperature uniformity, maintaining consistent thermal gradients in large furnaces is challenging, often resulting in different shrinkage. Long cycle times. Conventional sintering may require several hours or even days, reducing throughput. Grain growth control. Over-sintering can lead to abnormal grain growth, reducing mechanical strength and other properties. To address these challenges, researchers are exploring microwave sintering and develop microwave sintering, spark plasma sintering, or cold sintering methods that offer faster densification, lower temperatures, and improved microstructural control. However, these technologies remain difficult to implement at industrial scale due to equipment and cost constraints. The next is quality control and defect detection. Ceramic components are highly sensitive to microstructural defects such as pores, cracks, and inclusions, which can drastically reduce reliability. Scaling up increases the risk of such defects. Non-destructive testing methods like ultrasound, X-ray tomography, and laser scanning are increasingly being adopted to detect internal flaws early in production. However, implementation of these systems in line during high-volume manufacturing remains a challenge due to their cost and speed limitations. The next one is digital technology and process optimization for advanced ceramics. The integration of digital technologies can help overcome many bottlenecks associated with scale-up. Digital twins, artificial intelligence, and machine learning enable predictive modeling of ceramic processing, identifying optimal sintering schedules or detecting anomalies in real time. Data analytics can be used to correlate process variables with final properties, improving reproducibility. Additive manufacturers has also emerged as a promising route for scaling complex geometries with less waste. However, additive manufacturers still face a bottleneck in print speed, post-processing, and material qualification, particularly for high-performance ceramics. The next is the global ceramic industry also faces external bottlenecks that hinder scale up. Raw material availability. High purity ceramic powders are costly and sometimes difficult to source. Energy consumption. Ceramic production requires high temperature processing, making it energy intensive and sensitive to energy price fluctuations. Sustainability pressures. The push for green manufacturing adds new constraints such as the need for recyclable materials and carbon footprint reduction. Developing sustainable and energy efficient production routes is therefore critical to ensuring the scalability of ceramic manufacturing in future. Industries such as aerospace and biomedical engineering have pioneered in scale-up of ceramic for example, for turbine blades, implants, and coatings. However, even these sectors rely heavily on hybrid processes that combine conventional pressing and sintering with digital monitoring or additive fabrication. For instance, silicon nitride ceramics for aerospace bearing and zirconia toughened alumina for dental implants illustrate how advanced control and automation can enhance yield and reliability during scale up. Uh, In conclusion, we can say that for these bottlenecks, that scaling up ceramic manufacturing remains a multifaceted challenge involving material science, process engineering, and economic considerations. The main bottleneck lie in powder processing, sintering, quality assurance, and energy efficiency. However, the increasing adoption of digital and data-driven tools is gradually transforming the industry. By integrating artificial intellect-based optimization, advanced forming technologies, and sustainable energy practice, manufacturers can reduce cost and enhance scalability. Overcoming these bottlenecks is not merely a technical goal, it's essential for unlocking the full potential of ceramics in advanced application ranging it from healthcare to aerospace. On the first lecture, we discuss some examples of advanced ceramics, and now I will show you, I will discuss in this lecture how to develop smart materials, especially smart materials with crack healing effect in ceramics. Ceramics are among the most versatile materials in advanced engineering, prized for their high hardness, corrosion resistance, and thermal stability. However, their inert brittleness, their inherent brittleness and poor fracture toughness have long limited their structural application. In recent decades, the development of smart materials, especially ceramics capable for self-healing, has revolutionized this field. These materials can autonomously repair microcracks or damage caused by mechanical or thermal stress, extending their service life or reliability. The crack self-healing effect in ceramics represents a major advance in material science, merging structural integrity with the functional intelligence. Smart materials are systems that respond adaptively to external stimuli, such as heat, stress, or chemical changes. We discussed it in the first lecture. In ceramics, self-healing behavior enables the material to recover mechanical properties after damage. Much like biological healing in living organism, as we discussed it for concretes in the first lecture. This phenomenon not only improves durability but also reduces maintenance cost and enhances safety in applications such as for ceramics or concretes, especially for advanced ceramics which use for aerospace components, turbine engines and nuclear reactors, where used the thermal healing. Uh, Self-healing ceramics are part of a broader class of materials designed to detect, response, and adapt to environmental conditions. Unlike polymers or metals, ceramics don't exhibit plastic deformations, so the ability to autonomously heal cracks offer a transformative pathway to overcome their traditional weakness. The crack healing effect in ceramics is generally classified in two main mechanisms. Intrinsic, when occurs naturally due to materials composition and environmental exposure, as for cemented, and extrinsic healing, where specific healing agents are introduced to trigger repair under certain conditions. Here you can see the crack healing in advanced ceramics with from silicon carbide and silicon nitride as example. This is the one most widely studied mechanism, so-called oxidation-induced self-healing. Particularly, for example, silicon carbide and silicon nitride ceramics formed When a crack forms in this composition and is exposed to oxidizing atmosphere at high temperature, the silicon at the crack interface react with oxygen to form silicon oxide and heal the crack. In some ceramics, healing occurs through diffusion or partial transformation mechanism. For example, alumina-based composites have the same scheme of healing. Uh, with additives like titanium oxide or magnesium oxide exhibit grain boundary diffusion where atoms migrate to close microcracks during thermal cycling. Similarly, ceramics containing zirconium dioxide may experience transformation toughening when phase change at the crack tip absorb stress and inhibit propagation. The success of self-healing process in ceramic depends on several factors. The first factor is temperature. Higher temperature accelerate diffusion and oxidation. If we use the healing agent, uh, promotion healing. However, extensive heat may lead to undesired grain growth or further instability and destruction of the sample. The next one, atmosphere. The presence of oxygen or another reactive gases can facilitate or inhibit healing depending on the mechanism of self-healing. The composition, it means we have to select healing agent, the size of this healing agent, concentration, calculate the reaction kinetics of oxidation and distribution of this healing agent in the volume of composition. Optimizing this variable allows engineers to tailor self-healing behavior of for specific applications. Uh, uh, Self-healing effect and self-healing ceramics have some limitation. It's not suitable for all materials. For example, some limitation for this ceramics is high activation temperatures required for healing, difficulty achieving complete stress recovery in large cracks. It means that if the size of crack, the healing effect can't work for very large cracks. Complex microstructural design and the cost of material processing, its financial limitation. And limitation applicability in non-oxidizing or cryogenic environments where the self-healing effect not achieved. The next generation of self-healing ceramics will likely integrate multifunctional smart behaviors, combining healing with damage sensing, thermal management, and adaptive response. Advances in additive manufacturing enable precise control of microstructure, while artificial intellect-driven materials design can predict healing behavior under complex loading. Additionally, efforts to develop low-temperature healing system using novel oxides and glassifiers will make self-healing ceramics available in broader engineering contexts. The crack healing effect in ceramics represents a major leap toward intelligent, durable materials for demand applications by utilizing mechanisms such as oxidation, diffusion, and phase transformations. These materials can autonomously repair damage and restore functionality. Those challenges remain particularly regarding energy requirements and scalability. The concept of self-healing ceramics aligned perfectly with the goals of sustainable high-performance engineering. As research advances, smart ceramics are poised to redefine reliability standards across aerospace, energy, and electronic systems, bringing materials science closer to self-sustaining and adaptive structure of the future. And now I will show you my experience how to develop the self-healing materials for ball bearing. I start to develop the silicon nitride based ceramics with self-healing effect for ball bearing. The first step is to select the materials for these systems. It means the main material, the basic material, will be silicon nitride, but we have to select the healing agent for this composition. Uh, the incorporation of healing particles, usually metallic or non-oxide forming agents within a ceramic matrix, provides a mechanism for filling and sealing cracks through oxidation-induced volume expansion. In this case, this self-healing phenomenon enhances structural reliability, prolongate components life, and reduce maintenance costs in damaged applications. Uh, the crucial factor governing the efficiency of self-healing in ceramic composites is the relative volume expansion of upon oxidation. As you can see on this slide, it's a different material from titanium to some nitrides and carbides could be used for self-healing agent. But not all of them could be selected because the relative volume expansion of these materials is too low. Uh, when a crack forms in ceramic composite, as we showed earlier, the embedded healing particles located near the crack pass are exposed to oxygen or another oxidizing environment at elevated temperatures. The particles undergo a chemical oxidation reaction, producing an oxide phase that has a higher specific volume than the original metal or compound like or phase lot like titanium carbide or nitrides, etc. The newly formed oxide expands and fills the crack cavity, restoring structural continuity and preventing further crack propagation. The general reaction is reaction of metal or carbides, nitrides with oxygen. It's formed metal oxide with other volume of lattice volume. The efficiency of this process depends on thermodynamic stability of the oxide, kinetic rate of oxidation, volume expansion ratio, adhesion compatibility of the healing agent with the matrix chemistry and thermal expansion. The relative volume expansion upon oxidation is the ratio of a molar volume of the oxide to that the parent metal or compound. You can see this formula on this slide. How to determine relative volume expansion. If the relative volume expansion is around 1, minimal volume changes occurs. The healing may be incomplete due to insufficient oxide filling. If relative volume is more than 1, the controlled expansion can effectively fill cracks and bound surfaces. If relatively volume expansion is much more than 1, excessive volume increase and induce internal stresses, causing new microcracks or delamination. An ideal healing material exhibits moderate expansion around 1.2 and 2.5, sufficient to fill cracks but not enough to damage the matrix. The different materials could be selected using this formula, but calculating the relative volume expansion, I select the zirconium nitride as a healing agent for my composition with silicon nitride. And the next step to synthesize this composition. But you want to ask why we need to use this material. The proposed application for this material of silicon nitride with zirconium nitride, it's ceramic seals and sliding or rolling beers which work in extremal conditions, for example high temperatures or seawater. Replacement of metal components like balls, rolls in bearing onto ceramics help us to make bearings much lighter. It works better, and self-healing effect help us to enhance durability, lightweight, possibility to work in external conditions in high temperatures. Silicon nitride was selected because in composition with zirconium nitride, it's the healing agent it will be zirconium nitride, and it starts to oxidize at high temperatures around 500 centigrades. It helps us to operate this bearing at high temperatures. Silicon nitride is a traditional ceramic material for develop bearings and for high temperature applications. Ceramic ball bearings from silicon nitride are widely used in aerospace and high-speed mechanical systems. because they are lighter than steel, have lower friction, and resist to corrosion. Yet contact fatigue and surface microcracking remain critical failure modes under extreme speed and fluctuating of temperatures. Developed the self-healing composite from both from silicon nitride and zirconium nitride into bearing systems can drastically improve service life and reliability for these ceramics. Uh, Producing of these materials uh, include a lot of steps, and the first stage for the material is uh, thermal synthesis of composite powders with silicon nitride and zirconium nitrides. The objective of this stage is to obtain high quality composite powder mixtures as a raw material for self-healing ceramics. Uh, on this stage, thermal synthesis of silicon nitride with zirconium nitride composite powder have to be carried out without mechanical milling to uh, exclude additional contamination of ceramic by metal particles or other materials, ensuring chemical homogeneity and controlled particle morphology. The synthesis parameter, temperature, atmosphere, and holding time have to be optimized to achieve the desired phase composition. Experimental pilot batches have to be produced to define technological regimes for powder preparation. The next stage is consolidation. On this stage, we can use the up-to-date technologies like spark plasma sintering, or not novel but quite good technology of hot pressing. Uh, the main objective of this stage is to densify the synthesized powder onto fully consolidated ceramic bodies. The powders on this stage could be consolidated using hot pressing or spark plasma sintering method. Spark plasma sintering allows rapid heating and short sintering times, preserving the fine-grained microstructure and prevent the undesired grain growth. And I select this method because it have a lot of benefits. Special consolidation schedule could be developed to ensure effective densification of self-healing composite mixture. The final stage is a characterization of obtained composites. It means we have to determine the physical, mechanical, and self-healing properties of produced ceramics. Uh, Mechanical properties is flexural stress, hardness, fracture toughness. The thermal behavior include the self-healing efficiency, and as a ball bearing we have to additionally detect the tribological properties of these materials and continue. The first stage, thermal synthesis of high melting point composite nitride powders without milling. The development of high-performance materials from nitrides, particularly advanced ceramic composites based on nitrides, in one of the most promising directions in modern material science. Nitride ceramics such as silicon nitride, titanium nitride, zirconium nitride are known as their high hardness, excellent wear resistance, thermal stability, and chemical inertness. These properties may make them ideal for aerospace, energy, and mechanical application. Traditional processing of composite powder often involves mechanical milling to ensure homogeneity. However, mechanical treatment can introduce contamination, alter stoichiometry, and cause undesirable oxidation. Therefore, thermal synthesis without milling has emerged as a clean and efficient alternative for producing high-performance materials uh, composite from nitride powders with a controlled microstructure and high purity. Thermal synthesis refers to the formation of nitride phase through high temperature reactions between metallic, intermetallic, or oxide precursors and nitrogen containing atmosphere. The process is typically conducted in resistive furnace, plasma reactors, or controlled atmosphere chambers at temperature ranging from 1200 centigrade and higher. The absence of a milling step allows the natural formation of composite phase directly during the thermal reaction, eliminating contamination from grinding media and preserving the stoichiometric balance for these materials. The thermal synthesis of silicon nitride with zirconium nitride composite powder without milling represents an advanced contamination-free route for production high-performance ceramic materials. By relying solely on controlled high-temperature reactions, this method ensures chemical purity, uniform microstructure, and reproducible composition, all essential for the development of self-healing self-strength ceramic composites. Through further optimization, the scaling this approach can support the sustainable production of advanced nitrides for aerospace, energy, and industrial application, marking an important step towards the next generation of smart, durable ceramic materials. As we know, the silicon nitride with zirconium nitride composite system combines the excellent mechanical and thermal properties of silicon nitride with the toughness and oxidation driver self-healing potential of healing agent, which is zirconium nitride. The synthesis of this composite powder aims to produce a uniform, high purity, and fine-grained material for advanced ceramic applications such as aerospace, bearing, cutting tool, and self-healing components. The powder are typically produced through thermal nitration, where metallic silicon and zirconium react directly with the nitrogen in nitrogen gas at the temperature from 1000 grades up to 1200 grades. The thermal synthesis of silicon nitride with zirconium nitride composite powders we study in a solid state reactions between silicon nitride with zirconium. As you can see on this slide, it all provides in a semi-industrial furnace, and we can obtain low batches of the powders. As you can see on this slide, we analyzed the finally obtained synthesized composite powder silicon nitride with zirconium nitride. It on the first figure presents a particle size distribution, figure A. Curves for two synthesized composite powders containing 11 volume of zirconium nitride and 22 volume percent respectively. Both powders show a B-model distribution with the main fraction of particles centered in the submicron range. From half micron to 2 micron. This is ideal. What is ideal for sintering? The slightly broader curve from 22 volume percent of zirconium nitride sample indicates the presence of coarser zirconium nitride particles embedded within the finer silicon nitride grains. On the figure B displays the microstructure obtained using the electron microscopy of the composition silicon nitride with 22 volumetric percent zirconium nitride composite powder. Bright regions correspond to zirconium nitride grains, while darker area represents the silicon nitride matrix. The image confirms homogeneous dispersion of zirconium nitride particles through the ceramic matrix, with clear interfacial bonding and fine particle morphology. This uniform distribution is essential for achieving consistent properties in the consolidated material, and it's very important to achieve self-healing effect when the correct in material will be formed. The next step is consolidation of self-healed composites. The main idea of this stage it means that consolidation ensures that the densification in homogeneity in artificial bonding of the composite constituents, which are prerequisites of both mechanical stress and healing efficiency, will be achieved. Consolidation is a stage in material processing where the powder precursors are compacted and sintered to form a dense, mechanically stable solid body. In self-heated systems, especially those based on ceramics such as silicon nitride with zirconium nitride, the structure obtained after consolidation defines how healing phases are distributed and will be activated when the correct will be formed. As we discussed, it's a lot of consolidation techniques, but the most advanced technique which help us to densify material faster and at lower temperature, save the fine structure in to form a fine structure in material is spark plasma sintering technique. We select this technique for consolidation of these composites. But the next step is to develop special schedule for this ceramic. In our previous work with commercially available powders, we develop the special non-linear spark plasma sintering schedules for different nanocomposites. In present micrographs illustrate the microstructure of titanium nitride with silicon nitride, titanium carbonitride nanopowders, which was consolidated using spark plasma sintering technique and uh, non-linear schedules for this material. The nonlinear spark plasma sintering approach was proposed in our previous work. As I say, it's a novel modification of traditional spark plasma sintering when we try to optimize densification kinetics to achieve higher density to preserve the grain growth. It means that we develop the special regimes with a different stage. This approach demonstrates that we have to change the heating rate, the loading regime during spark plasma sintering, and we can control the grain growth, the evolution of pore structure, and effectively tailor the microstructure, especially for nanocomposites of high melting point compounds, reducing grain growth and improving mechanical performance compared to traditional sintering. We apply this technique for consolidation of composition synthesized silicon in situ synthesized silicon nitride with zirconium nitride. We added the special oxides to activate the densification process. The sintering behavior of silicon nitride-based composites strongly depends on the heating regime, powder composition, and presence of oxide additives. In our study, the silicon nitride with zirconium nitride, we added the yttrium oxide and aluminum oxide to composite system and consolidate it using spark plasma sintering. The results reveal efficient consolidation, homogeneous microstructure, and improved distribution of healing agent. Demonstrated the potential of SPS for development highly dense self-healing ceramics. We densify it in relatively low temperatures up to 1650 centigrade and characterize the microstructure, and here you can see that healing agent is the zirconium nitride is homogeneous distributed in the volume of the composite from silicon nitride. Despite the promising results, several challenges remain that must be addressed for industrial scale production and optimization of self-healing composites. It's develops of specific press instrument, because here we uh, uh, consolidate only the cylindric specimens, but for develop the bearings we have to construct the special dies for the balls. The next one is optimization the sintering schedules for different composition based on silicon nitride and zirconium nitride. Uh, but in conclusion, we can say that SPS consolidation for these materials successfully produce a dense, homogeneous microstructures with a well-distributed healing agent. The observed densification and shrinkage behavior confirms the efficiency of these methods for fabrication of high-performance self-healing ceramics. However, further development of custom press tool, optimized schedules, and thermomechanical processes is essential to adapt the method for various composition and geometries. These improvements will ultimately enable scalable production of reliable self-healing materials for aerospace, energy, and advanced mechanical systems. The next step as, is the development of special tools. As I say on a previous slide, it's a problem. We developed the special press tool from graphite to obtain the ceramic balls. Here you can see the SPS consolidated samples in a near ball shape, and this consolidated by SPS samples could be polished for precisely for balls, for ceramic balls with a specific diameter around 13 millimeters in diameter. These balls have a high relative density. Material has high relative density around 97% from theoretical high Vickers hardness and fracture toughness. And the next stage is materials testing. The evaluation of self-healing ceramic composites requires a comprehensive understanding of mechanical and tribological behavior before and after a healing process. This test confirms whether the material can efficiently restore its properties after damage and maintain performance in harsh environments such as high load in balls or some energetic or mechanical system. The first test we proceed is a high temperature bending test to determine the residual strength and healing efficiency of ceramic after exposure at elevated temperature. When cracks form, oxidation of embedded healing agent zirconium oxidizes and seals the crack to restore a loading bearing capacity. Self-healed silicon nitride with zirconium nitride composites can recover up to 80 or 90% of original strength after thermal treatment. The next test is hardness. Vickers hardness or non-indentation hardness testing reveals a surface integrity and densification quality of cell heal zone. After healing, the formation of oxide or glassy sealing phase often leads to increased local hardness, indicating successful bonding and crack closure. And friction behavior. Tribological testing under dry or lubricated condition evaluates the friction coefficient and wear rate before and after healing. The formation of oxide films on the surface during self-healing acts as a solid lubricant layer, reducing wear and friction. This property is essential for moving components like bearing or cutting tools. Mechanical testing of cell-healed materials demonstrates that controlled oxidation and microstructural design, which we developed from the powder through the consolidation methods, allow ceramics to regain mechanical integrity, maintain hardness, and reduce wear even after several damage. This finding confirms that self-healing composites can operate safely and efficiently under extreme mechanical and thermal stresses, marking a crucial advancement in smart and durable material design. As we can use this material for as a ball bearing, we have to make a tribological tests, but for tribological tests is the main uh, problem to select the suitable counter body. It could be some hardened steel, alumina, tungsten carbide, etc. Ensures that controlled testing and helps to replicate real service condition. Uh, we test our material with steel and hard alloy and with the same titanium nitride and silicon nitride nanocomposites to select what the most suitable material, counterbody material to produce fully ceramic bearing or produce hybrid bearing. In conventional bearings, metal components such as steel balls and races commonly made from bearing steel operate under high contact pressure and frictional loads. During prolonged use, these parts are exposed to mechanical wear, oxidation, and micro-welding, leading to surface damage, increased friction, and eventually failure. The image clearly shows a tribological contact between bearing steel counterbody and silicon nitride based nanocomposite surface, where steel experience several material transfer and abrasion. This degradation not only reduces bearing lifespan but also increases maintenance cost and limits performance for high temperature or corrosive environment. Over these challenges, the concept to replacing traditional metallic components with self-healing ceramic composites has been proposed. Materials like silicon nitride with additives of zirconium nitride or titanium nitride nanocomposites exhibit excellent hardness, oxidation resistance, and wear behavior. Under operation condition, when microcracks or wear-induced damage occur, oxidation of embedded nitride phase produced oxide films that fill surface defects, efficiently healing the contact zone. These mechanisms restore smoothness, reduce frictions, and protect the underlying structure. Replacing steel with self-healing ceramic allows bearing to operate at high temperatures and reduce lubrication and in corrosive or vacuum environments, conditions where metals typically fail. Moreover, the lower wear rate and self-repair ability significantly extend service life and reliability. The wear of metallic bearing components remains a key limitation of achieving long-term durability and efficiency. The transition of self-healing ceramic nanocomposites provide a transformative solution, combining superior tribological performance with autonomous surface restoration. This approach paves the way for the next generation of smart, maintenance-free bearing system in aerospace, automotive, and industrial application. We investigate different materials, as I say, not only Berenstein, but the ceramics counterbody and tungsten carbide based counterbody. And we investigate the surface of different counterbodies after tribological test in dry wear. The figure presents a comparative study of surface condition before and after tribological tests of hard alloy and silicon nitride based nanocomposites under dry sliding condition. The objective is to analyze wear mechanism, surface morphology, and potential of ceramic composite for bearing solution. The image on the left shows a hard alloy counterbody surface that has been subjected to dry sliding contact with the silicon nitride nanocomposites. The initial surface appears relatively smooth, but after the test, the idea of tribological contact exhibits pronounced wear tracks and plastic deformation. The corresponds 3D surface topography bottom left confirms significant surface roughening and material loss due to the adhesion and abrasion. On the surface formed the special in the area of tribological contact formed the layer which contained not only hard alloy but the debris of ceramic, nanoceramic, and its decrease in the future the wear of system and the friction coefficient. On the right figure shows silicon nitride composite surface, counterbody surface after tribological testing against a similar nanocomposite counterpart. The initial surface is fine and uniform, while the area of tribological contact displays only minor polishing and microscale deformation, suggesting low friction and minimal wear. It means that the best to construct the fully ceramic bears, but it's a high cost. It means that preferably to construct the hybrid bearing, but if it possible, the ceramic part is better. It shows the superior wear resistance and surface compatibility. In conclusion, the comparison clearly demonstrates that ceramic contact provides much better tribological performance than metal ceramic contact under dry wear condition. The silicon nitride nanocomposite show remarkable resistance to wear and maintains surface integrity, making it a strong candidate for bearing and sliding components in the extreme environment. But we have to uh, calculate the cost for these materials and before construct on the bearing, as I said, on the next step. And next step will be construction of ball bearing elements. Uh, uh, to overcome this drawback, researchers have developed self-healing ceramics. We developed self-healing ceramic composites that are capable to autonomously repair and damage during service through controlled oxidation reactions, as I say earlier. Among these materials, silicon nitride with zirconium nitride composites stand out for their excellent combination of mechanical properties. Here you can see the mechanism of self-healing, the effect of self-healing for the ceramic based on silicon nitrate. Here the defect with a 50 micrometers width, and when we expose it at high temperatures around 500 grades or 550, the crack could be healed among 5 hours. We construct the ball bearing from ceramic balls based on silicon nitride with zirconium nitrate as healing agent. Here you can see that zirconium nitride oxidized in these ceramic composites formed the zirconium dioxide layer which healed the defect. But healing the defect is not the main for this material. The main for this material that the mechanical properties and tribological properties of this bearing will be the same as for non materials without defect. And we tested, it shows that the flexural strength for these materials is the same after healing the defect. It's around 400 MPa. Uh, uh, By contrast, silicon nitride safe-healing ceramics can maintain functionality even in absence of oil for this material, as the oxidation-driven healing process restores a microcracks region in real time. This enables long-term operation at a high temperature. It means in oxidizing atmosphere. At the temperature around 500 to 700 grades, with a significant, without significant degradation. The hybrid bearing design combining ceramic and metallic component allows for weight reduction, thermal insulation, and improved energy efficiency for this material. Furthermore, the self-healing property ensures predictable service life and reducible maintenance requirements, which are essential for uh, aerospace, defense, and high-speed mechanical synthesis. The self-healing phenomena in silicon nitride, zirconium nitride ceramics represent a major advance in the field of smart materials. Its scientific and technological significance lies in the several aspects. The healing process occurs spontaneously under operating conditions without a need for external intervention or added materials. The oxidation of zirconium nitride provides an internal repair mechanism that prevents crack propagation, thereby extending the lifespan of components. The material operates efficiently in air and doesn't require oil-based lubrication, reducing environmental impact. The ability of repair itself in service minimizes downtime and replacement cost, offering long-term economic advantages. The study and demonstration of self-healing effect for these ceramic composites highlight a transformative approach in advanced materials engineering. Through the controlled oxidation of zirconium nitride particles, cracks could be autonomously filled by zirconium dioxide, as I say, leading to complete restoration of surface integrity and relatively low temperatures. This phenomena enabled to develop the class of new smart self-sustaining ceramic materials suitable for high-performance applications. When applied a hybrid bearing system, such material offer unprecedented resistance to wear, oxidation, and mechanical degradation, allowing continuous operation at elevated temperature without lubrication. And the next step is the quality control, standardization, and reliability for these advanced ceramics. As quality control in ceramic focuses on ensuring that every step from raw material preparation to final inspection meets stringent power performance and safety criteria. Unlike metals or polymers, ceramics don't exhibit plastic deformation before failure. This means that even microscopic flaws such as pores, inclusions, or microcracks can lead to catastrophic fracture under stress. The key quality control objectives include material purity, monitoring of chemical composition and particle size distribution of ceramic powders to ensure consistency, process stability, maintain precise control over forming, sintering, and finishing parameter defects detection, using advanced inspection techniques to identify structural irregularities before they compromise product integrity. This quality control serves not only to verify product performance but also to prevent costly failures in critical applications such as turbine blades, armor systems, or dental implants. To ensure high quality ceramic components, manufacturers increasingly rely on non destructive testing methods. These techniques enable inspection without damaging of the part, which is vital for costly or complex components. Common non-destruction testing techniques include ultrasonic testing, defects, internal cracks, and delamination by measuring sound wave reflections. X-ray computed tomography provides 3D imaging of internal microstructures, allowing precise mapping of porosity and inclusions. Infrared tomography identifies thermal inconsistencies that indicate internal defects. Optical and laser scanning used for dimensional accuracy and surface roughness evaluation. Recent advances incorporate machine vision and artificial intellect based defect recognition, which improve detection accuracy and enable predictive maintenance of equipment. Integrating digital inspection data with manufacturing analytics allows for closed loop process control, ensuring consistent quality in high volume production. Standardization provides a framework for uniform production and certification for advanced ceramic international standards. Organizations such as ASTM International, ISO, or ES establish guidelines governing materials processing and performance testing. Standardization ensures comparability between laboratories and manufacturers, facilities global trade, and promote trust among suppliers and end users. In the industries like aerospace and medical devices, adherence to standards is not optional. It is a prerequisite for certification and regularity approval. To maintain high levels of quality and reproducibility, advanced ceramic manufacturing increasingly employs statistical process control. Statistical process control uses data collection and analysis to monitor process variation, detect trends, and prevent defects before they occur. Techniques such as Six Sigma are designed for experiments and process capability analysis help identify sources of variability and optimize parameters. Reliability is the ability of a ceramic component to perform its intended function over a specified period under given condition. Because ceramic fail in a brittle manner, reliability prediction must account for statistical variation in flow size and distribution. The Weibull statistical model is widely used to describe the probability of failure in ceramics. Reliability testing is particularly vital for applications where failure is unacceptable, such as gas turbines, medical implants, nuclear reactors. Through modeling and testing, manufacturers can predict service life, reduce over design, and ensure safety. Modern quality management for ceramic increasingly incorporate digital twins, artificial intellect-based analytics, and machine learning to monitor complex processes. A digital twin, a virtual replica of a production line, can simulate and optimize every step from powder preparation to final inspection. Artificial intellect algorithms analyze vast amount of sensor data, identifying correlation between process variables and final properties, thus enabling self-optimizing systems. Moreover, blockchain technology are being explored to enhance traceability, ensuring every material to process step is verifiable and compliant with regulatory requirements. Future development aim to create fully automated artificial intellect driven quality system capable of real-time defect prediction and adaptive process control. The convergence of material science and digital technology promises a new generation of ceramic manufacturing that is smarter, more efficient, and highly reliable. The next is supply chain cost and material availability issues in advanced ceramic. Uh, the performance of advanced ceramic depends heavily on the purity and availability of specific raw materials. Elements such as yttrium, zirconium, boron, aluminium, and rare earth oxides are critical for producing ceramics these samples of advanced ceramic. However, these materials are oversourced from limited geographic regions, creating vulnerables. Supply chain is quite hard. For example, rare earth oxides, vital for electronic and optical ceramics, are predominantly mined in China, which controls a large portion of global supply. Ceramic production is inherently energy demanding due to high temperature processing. Ceramic production is inherently energy demanding due to a high temperature process such as calcination, sintering, and hot pressing or spark plasma sintering. Typically, sintering temperatures range from 1000 to 2000 grados, requiring prolonged heating cycles and substantial energy input. In some cases, such as silicon carbide or alumina ceramics, even high temperatures are needed to achieve full densification and desired microstructural properties. These high energy requirements significantly affect production cost and carbon footprint. In periods of rising global energy prices, ceramic manufacturers face financial strain, particularly in regions where energy is not subsidized. Additionally, achieving uniform heating and cooling is critical. Any temperature variations can lead to cracks or internal stresses, increasing scrap rates and waste. Emerging technologies such as microwave sintering, spark plasma sintering, and cold sintering show potential for reducing energy consumption. The balance between cost efficiency and material performance continues to be one of the most pressing challenges in the ceramic industry. Producing advanced ceramics requires highly specialized and often customized equipment, including high-temperature furnace, isostatic presses, precision grinding system, and non-destructive testing instruments. All of this is quite expensive and increase the price for the final product. In addition to technological challenges, the ceramic industry relies heavily on a highly trained specialist who possess expertise in material science, thermal processing, and failure analysis. The multidisciplinary nature of ceramics, bridging chemistry, physics, and engineering, requires professionals capable for understanding both theoretical and practical aspects of material behavior. Uh, At the same time, environmental concerns under pressure to develop sustainable sourcing and recyclable strategies. The extraction and processing of raw materials such as some high melting point materials generate considerable waste and greenhouse gas emissions. It's to increase the uh, price for materials, final materials. The production of advanced ceramic is constrained by a complex interplay of material availability, energy consumption, equipment dependence, and labor expertise. Limited access to rare raw materials and high energy intensity of processing and reliance of specialized infrastructure make a large-scale manufacturing both costly and environmentally challenging. Overcoming these obstacles will require coordinated efforts between industry, academia, and policymakers. By embracing innovation in material science, process optimization, and sustainability, the ceramic industry can enhance its resilience, reduce cost, and secure a sustainable future in an increasingly resource constrained world. The production of ceramic is inherently resource and energy intensive. Processes such as raw materials extraction, powder synthesis, and sintering consume large amount of energy and contribute to greenhouse gas emission. The sintering process, where ceramic powder are densified at temperature up to 1080, for example, 100 grados, accounts for a majority of energy use. Conventional furnaces rely on fossil fuels or electricity generated from non-renewable sources, resulting in significant emission of carbon dioxide. For instance, the production of alumina or zirconia ceramics can emit up to several kilograms of carbon dioxide per kilogram of material produced. Ceramic production depends on minerals such as rare or earth oxide, silica, etc., which are often mined in environmentally sensitive regions. The extraction and refinement process lead to soil degradation, water pollution, and high waste generation. Moreover, some high-performance ceramics incorporate elements like yttrium or neodymium, which are classified as critical raw materials with limited global reserves. Ceramic processing generates dust, off gases, and slurry wastes. Improper disposals of these byproducts can contaminate water and soil. The use of binder solvents and additives in shaping and glazing introduce chemical pollutants and requires careful handling and treatment. To mitigate these issues, manufacturers are increasingly adopting cleaner production technologies such as microwave sintering and other sintering to produce to make this production much cleaner and decrease energy consumption and waste. Uh, Addressing environmental life cycles issues requires a combination of technological innovation, regularity, enforcement, and industrial collaboration. We have to develop green manufacturing, eco-design principle, digitalization policy, and collaboration. Moreover, as an example, I show you we have to develop modern smart materials, materials with self-healing, materials with long-term resource of exploitation. Uh, The environmental regularity and life cycle aspects of advanced ceramic are integral to the responsible growth of the industry. While ceramics contribute to energy efficiency and technological progress, their production remains energy intensive and resource dependent. Regularity frameworks across aerospace, defense, medical, and energy sectors ensure safety and compliance, but they also impose additional costs for complexity. The recyclable of ceramics continues to be a major challenge due to their inherent chemical stability. Future progress lies in the adoption of green processing technologies, standardized regulations, and critical economy approaches by addressing this issue holistically. The ceramic industry can achieve sustainability without compromising on innovation and performance. And on the next lecture, we will discuss this route how to develop green processing technologies in different technology readiness levels. And now the lecture is over. Thank you for your attention. If you have any questions, please contact me.